Okay, well, first slide is all about me. This is what I do for a living. I am an academic, which I know is disappointing for most of you because academics can't actually do anything. I spend about half my time being a professor and about half my time doing consultancy work for people like the Bank of England, Sainsbury's, anybody with money, basically, you know, within reason. Actually, I say that. Anybody moderately ethical with money would be fairer. So, for those of you who don't know, this is my life, sadly. My life is data, that's it. That and restoring old cars. So it's a sad life, but I enjoy it. We're going to talk about neural networks. And I should have said in the introduction I wrote that the assumption is you've come here not knowing anything about neural networks. If you are an expert in neural networks, you will be mind-numbingly bored by this talk. If you don't know anything about them, I hope to move you to a state where you do understand a bit more about them. Just to give you some very brief background, the idea for neural networks was invented. Do you invent an idea? Discovered? Came to somebody in about 1946. We didn't get them working properly until 2012. That tells you either that a lot of people are very, very stupid, or it's actually quite hard to get them working. It's quite hard to get them working, and the underlying maths is mind-numbingly complicated. We are not going to do any of the mind-numbing maths. Some of you will be appalled by that, but most of the audience is probably going, oh, thank God for that. So we're not looking at it from a mathematical perspective. It's a very, very interesting way of looking at neural nets, but it is not necessary to understand the maths to be able to use them, or indeed to understand how they work. I'm not saying it's not useful to understand the maths, but it's not essential. So where do we start? Well, you're probably all familiar with data mining, he said, hopefully. Data mining is automated looking for patterns in data. We're going to take a look at an example of that because we're going to solve it using a normal data mining algorithm. Then we'll look at it, what happens when you use a neural net. The Titanic data is a classic data set for data mining. I use it unashamedly, actually, because some of you may have come across it already. And if you haven't, everybody has heard of the Titanic. And I haven't seen the film, but even I know that you're supposed to go at this point, and then everybody knows which ship you're talking about. We have very good records of who was on the Titanic. We have good records, very, very good records about who survived and who died. And we have very good information about a lot of background information, their sex or gender, their age, the class they were in, and so on. So it's quite an interesting set to look at. And you can data mine this, trying to see what factors led to survival or death. And this is very well known. There's nothing earth-shattering in this. The R code to do this is unbelievably simple. The Python code to do it is unbelievably simple. It's very easy to do this. If you do that, you take that data and you pass it through a decision tree algorithm. How many of you have done this, played around with decision trees? Okay, yeah, it's fine. I'd guess most of you have. What you find is a pattern, and the pattern is very easy to understand. And this is really good if you're doing data science and you're working on data for clients. It's very nice to use decision trees because everybody can understand them. You can present the data to users and they go, yeah, I can see the pattern. So I looked at 1,043 passengers. There were more, but we have incomplete data on some of them. And of those, the most important decider about whether you survived or died was your gender. If you were male, there were 658 males. If you were male, you had a 21% chance of surviving. If you were female, you had a 74% chance of surviving. Interestingly, in terms of decision trees, the next layer down does not have to be symmetrical across. So if you're male, the most important thing to be was to be young. Being an adult male was a bad choice at that point. If you're female, age had nothing to do with it. The class in which you had signed up was significant. If you're young and male, being in a big family is a really, really bad idea. Why do you think that was? Say again?
Stay together.
Yeah, you can imagine a situation, I don't know is the answer, but you can imagine a situation where a mother has 3 or 4 children, she's trying to keep them together, trying to get them all onto one boat at one time and failing. A mother with one child is carrying the child and getting into a boat. So that's supposition on my part. The whole point about this is that data mining with things like decision trees is very easy to do, and it often yields stuff that is quite easy to understand. Not always, but it's generally true. So data mining is interesting because we are using a computer program to induce a set of rules. And I make this point because mostly what we do in computing is a human being sits down and induces a set of rules and then programs it into the computer. If this is true and that is true, then you should do this. The human being has worked out what the rule is, and they type the rule into the computer program, and the computer is just following instructions. When we move into things like data mining, neural nets, what we're doing is getting the computer to work out what the rules are, and that's what's going on here. The computer is deciding what are the important rules here. So there are lots of data mining algorithms around there. In general, they produce easy to understand, and they're easy to communicate. There are times when we want the machine to learn and then apply the induced rules to new data. And if you want my idea of the difference, in data mining, you're saying, show me the pattern. In machine learning, you're saying, show me the pattern, remember the pattern, throw away the data, keep the pattern, and then we can apply that pattern to new instances of data. So in insurance fraud, we take a load of cases where a human being has said, this one's fraud, that one's fine, 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 fraud, fine. We feed that into some kind of algorithm. The machine builds some kind of model of what fraud looks like. That model may have looked at 10,000 cases. We can throw the cases away as far as the machine is concerned. Just keep that model, and the model can be tiny compared with the data. Then we take a new case, we feed it in, and the machine says fraud. So, difference between data mining and machine learning. Linear regression is a beautifully illustrative example. I might have 1 million data points there. I can produce a line from it, and I can then throw the data away. And all I keep is the y equals mx plus c model of that line. And I can then apply it to new cases. Somebody can say to me, if we spend £23,000 in marketing, how much additional profit will we make? And the answer is 50,000. So we're applying that model to new cases. So this is not just about linear regression. If you look at autonomous cars, which for me are a good example of this kind of difference, I cannot conceive of an autonomous car programmed with a series of instructions from a human. Good rule we should program in. If elderly professor, then avoid at all costs. You don't feed in a set of rules. What you do is drive the thing around and get it to learn how to avoid hitting things. That's how it works. So this is not sort of slightly better. This is enabling us to do things we simply cannot do with the old way. Old way, human beings induce rules, type them in. New way, the machine induces the rules. So we have a range of data mining and machine learning algorithms, but this much more generalized approach of neural nets, these are fascinating devices. And they are really quite different in quite a lot of ways. So, 1940s, people came up with this idea. They said, we know how the human brain works. Why don't we make a computer or machine that behaves like that? Incidentally, my original degree and PhD were nothing to do with computing. And I ended up at one stage working in a neuroanatomy department in Dundee, actually. And I learned the fastest way to irritate neuroanatomists was to start a sentence with, given that we know how the human brain works, we can, it drives them crazy. and they know you're winding them up, and they still can't resist it. So we do not know how the human brain works, but we know it's got little neurons and they fire and so on. We know something about it. 1940, the idea was produced. It wasn't until 2012 that this guy, Geoffrey Hinton, actually made a neural net that worked sensibly. Now, I gave this talk, or a variation of it, in a university, and somebody in the audience went wild at this and said, I was making neural nets that worked in the year 2000. Okay, this comes down to the definition of does something sensible. Because I was making neural nets work in the 1980s, and they could do nothing. I was going to say bugger all, but I stopped myself in time. Oh, I showed it. What Geoffrey Hinton was getting them to do was to identify pictures, tell cats from dogs. Okay, that's trivial, but the implication of that is huge. It is really hard to do this. Geoffrey Hinton received a Turing Award recently for that work. Turing Award being the computing equivalent of Nobel Prize. This is seriously hard to do. And that's where a lot of the maths comes in. So, anybody know who his great-great-great-grandfather was? It's fascinating. It's George Boole, as in Boolean logic. See, genes will out. You see that? So I think neural nets are a very big part of the future of the work we're going to do. We've seen them come of age after an incredibly long gestation period. They are now extremely powerful and extremely potent, and they're not being used effectively yet. So, I don't want to bore you with the biology, but we have neurons in our head, we have cells. And the cell is either sitting there quiet or ping, it's firing a message down that long axon down there. So they can transmit information. The cell can either be sitting at rest or ping, it fires a pulse down there. In fact, each neuron doesn't sit alone. This neuron connects to that one. This one has ones connecting to it. And they have millions. You have millions of these things in your head. Uncountable millions. There are estimates, but nobody really knows. There are lots and lots and lots of these guys in there. And if this one fires, this one may not. But if this one and that one fire, then this one will fire. So these things, in your brain constantly, these things are firing, and that's what thinking is. So we understand how the human brain works. Sorry, I was just testing if there are any neuroanatomists in the audience. So what we can do is say, well, we could build a model of that in software, and that's what a neural net is. And the simplest kind of neural net you can build has this great name. It's a perceptron. Now, you can tell this was named in the 60s. This is the era where they had jet fins on cars, and kryptonite was invented, and perceptrons. Isn't that a great name? Charles, turn on the perceptron. I mean, I think it's a great name. So, the simplest one we can have is this. It's perceptron. Essentially 3 neurons. They're artificial neurons, but we're going to make them behave pretty much like real ones. Now, what I'm going to do is walk you through using this simplest possible network to do some honest, real work, to get it to do something. So I want to tell you how neural nets work, and it's an incredibly simple model. It's very difficult to implement, but that's not the point. Basically, you put numbers in here, you multiply each of those numbers by some other number here, you sum them, and that gives the answer. And you're thinking, he's lying, it's more complex than that. No, I'm not. This is how a neural net works. So, for example, let's allocate the number 4 there and the number -2 there. And you're also thinking, well, you don't really allocate them randomly, do you? Yes, you do. Actually, at the beginning of a neural net, these numbers are called the weights, incidentally. These weights are allocated randomly. It's spooky, but true. Okay, so if I put the number 6 and number 3 in there, this is going to be purely mechanistic. You can work out the answer now. 6 times 4 is 24. 3 times -2 is -6. Sum those, and you get the answer 18. And that's what a neural net does. Now, on its own, that's not going to do anything because it's just going to give you a summation, and you could have done that in Excel. Sorry, I'm not trying to insult you as data scientists, but it could have been done in Excel. So you have to wrap a process around that. That's fair. We can wrap a process around it. For that, we're going to need some data. And there is another classic set of data called the iris data set. Again, I would reckon a lot of you are familiar with it. You may not know its origins, which are fascinating. So there are, irises are very beautiful plants, I think. And if you're a botanist, and some of my background as being a botanist, you can spend a lot of your time, and part of my PhD was spent measuring the morphology of flowers. So I have some empathy with this data set. And these are sepals, and you can measure the length of the sepal, and you can measure the width of the sepal in different species. I'm not suggesting any of you take this up as a hobby, but I'm saying that you could do it. And a wonderful guy called Fisher. Now, this guy Fisher is famous in statistics and genetics. He had a mate called Yates, and they produced a book called Fisher and Yates. And you can tell a really influential book when it's known by its authors and not the title. And I don't even know what the title of it was. It's always called Fisher and Yates. And he published a paper, not a book. The use of multiple measurements in taxonomic problems is an example of linear discriminant analysis. He was both a biologist and a statistician, very good statistician. And so he collected this data. He took 50 examples of species. Actually, he did 3 species, not 2. We're only going to use 2. Iris setosa and Iris versicolor are the ones we're going to be playing around with. And I'm showing 4 measurements here. He took 50. He measured 50 plants. But I'm going to use this data to show you how a neural net works. And just for your comfort, really, if you plot sepal width against sepal length, it is quite clear that these species are morphologically different. There's a cluster there and there's a cluster there. And in fact, crucially, you can get a straight line between them. So is everybody happy with that? I mean, it's just saying that in setosa, that sepals tend to be wider and shorter. So it's not rocket science, this. So, okay, we have our neural net. Well, it's a perceptron, which is a tiny neural net. We allocate weights completely at random. They're just generated. We then take that first set of numbers from here, and we feed them into the perceptron, and it does its magic. It sums them and produces an answer. Okay, and completely arbitrarily, we say, we want the answer, when we feed in setosa data, we want the answer to be 1. And when we feed in versicolor, we want it to be 0. And interestingly, you could reverse that choice at the beginning. It doesn't matter which way round you do it. So that's an arbitrary choice as well. Once you've chosen it, you have to stick with it, but it's arbitrary. Now, you will notice this is producing a very bad answer. It's smack in the middle. It's no use at all. Okay. So this whole system is now under control of the neural net, which is a process running. It feeds in the first numbers, multiplies them by the random numbers, gets the answer, and it should be very unhappy with the answer. I am anthropomorphizing here. Software does not get happy or unhappy, but you get the idea. Well, it can't change the numbers over there because they are fixed. What it can change is the weights, so it does. It changes the weights slightly to see if it can get a better answer. So we change the weights, we get an answer, we've changed the answer. That's now a bit too high, but what can we do? You're all getting in the groove here, aren't you? Well, it changes the numbers again. And lo and behold, it gets it fairly close to 1. Okay, now it doesn't make it exactly 1 because it's got to get them all working. So it gets it close enough. Then it may feed in a versicolor. And what it's trying to get now is 0. Okay, with those weights, this is way too low. So, okay, it tries again. And what it does is repeatedly go back over all the numbers, fiddling around with these weights, until, on average, it'll get approximately the right value for each species. And therein actually lies the rub, because I've just said it'll go on doing that until it gets it right. On a perceptron, that's possible. On the large neural nets I'm going to show you, that is trillions of possible numbers. And that's what it took us so long to crack mathematically, was how do you not do every possible combination? How do you optimize to find the correct values? And that's a process you can look up, which is called back propagation. And that was an incredibly clever way of tunneling under that mountain of calculation that had to be done. So there is the tricky bit. But with our little one, it can do it. Okay, that in essence is how a neural net works. Now, first run through, I left out 3 details. And given we have plenty of time, I'll go back and add in the details, because I don't like lying to people. When I've added in the details, it is truly a working neural net. And actually, that'll work. It's going to be wildly suboptimal, and it's going to take a long time to actually work. So we can improve on that dramatically. First thing we do is we normalize the input data. So we just scale all the input data so every value is between 0 and 1. And what that tries to do, or what that does do, is if you're feeding in numbers, you might have big numbers, like, I don't know, the height of a person in centimeters, and you might have small numbers like the number of noses they've got. And that big number mathematically or arithmetically will overwhelm the smaller number, so it makes them all contribute equally. That's all it's doing. So if you take those numbers and we normalize them, they are all between 0 and 1. And just in case you begin to worry about this, because you might think the maximum sepal length is actually that one. The lowest sepal length is 4.3, so something like 4.7 comes out as close to 0, but that's fine because it's near the lower limit for that number. So all we've done is scale these. There's no, that's incredibly easy to do. So we scale them to between 0 and 1. We normalize the data. So just to show you that all that means is that the numbers you feed in are between 0 and 1. It's still doing the same thing. And I've changed this to this sigma, which means mathematically sum. Everybody happy with that? I mean, it's just a trivial difference. We scale the output data. It turns out that it's very effective if you make sure that the number coming out of the neuron is also between 0 and 1. So that's okay. We apply a scaling function to that. And for those of you who are interested, I only mention this really because they're called squashing functions, which I think is a wonderfully non-technical term. Go on, let's apply a squashing function to it, and it just squashes it. And it also, this particular squashing function, which is quite commonly used, not always, has this thing called Euler's number in it, which always seems to me like you ought to be asking his permission to use it, but he's dead now, so he's fairly relaxed about that. But basically, what that means is no matter what number you feed in, it will always come out to be either just under 1 or just over 0. And okay, I've only fed in the numbers from -6 to 6, but if you feed in 1,000,000, it will still be scaled between 0 and 1. Everybody happy with that? It's just a convenience, because what we're going to do is take the output from this neuron and feed it into another one as we build bigger chains. So if we want to scale the input numbers, we actually have to scale the output numbers because they're going to be the input numbers on down. So really, these are not 2 things we're doing, it's just 1. We're just scaling the numbers, keeping them under control. So that is it, summation. In fact, we take that sum, we put it through a squashing function, and it comes out between 0 and 1. Still the same principle. Final thing is that we don't have to, but we very often have what is called a bias neuron, and that is another neuron which always squirts in the figure 1. And there's our perceptron. we add a bias neuron here, which always squirts in 1, but it has a weight as well, and the neural net is allowed to tweak that one as well. And if anybody's interested afterwards, I can give you an explanation as to why that's sometimes useful. But it's just something we do. And you don't have to do it, but it just makes it more efficient. So feed in those numbers, play around with the weights. The neural net can play around with this weight as well. Sum, squish, get the output. The bottom line is that that perceptron, genuinely that perceptron, can distinguish between versicolor and setosa. So in other words, this is actually a neural net that I built. I say that grandly. I built a neural net, you know. I just used R code to do it. I mean, it's dead simple to do this. I fed in the data, and the actual numbers it requires are minus 21 point blah, and 18 point blah, and 0.4 blah, and that is able to distinguish between versicolor. It actually works. I think it's incredible that that works. I'm still gobsmacked that that simple mechanism. So if you feed in those numbers, and then you take a real versicolor and you feed it in, it'll say versicolor. You feed in setosa, and it'll say setosa. Does it always get it perfectly right? It depends how big a training set you give it. If you give it enough data, it'll get more and more of them right. You might occasionally, if you remember that graph, you might occasionally get one that is below that line. If we trained it with that, it would separate. Basically, if you can draw a line between the sets of data, it will be able to tell them apart. I think that's, I love that. I've always loved that. How can that work? That's brilliant. So these perceptrons will actually work. Now, I doubt you want to use neural nets to identify plants. Can we do something like predict who will survive and who will perish on the Titanic? The answer is yes, you can. You're going to feed in some data. I've chosen, I think, 7 of the parameters. The class, the gender, the age, how many siblings they had, how many parents they had on board, what fare they paid, and where they embarked. If you feed that lot into a neural net, now you notice I've got to have more of these input neurons. And I haven't named these yet, so I'm going to name them now. For every type of data, for every column of data you're going to feed in, you need an input neuron. That's where you put the number. You can then have what's called a hidden layer, and you can have as many hidden layers as you like. I could have 2, 3, 4 hidden layers. And you have an output layer. And I'm using this output layer to output 1 if they survived and 0 if they died. You don't have to be classifying binary things. You could be classifying things as A, B, and C, or A, B, C, D, in which case you would have 4 output neurons. But this, again, is a real neural net, and those are the numbers. And that neural net is not as good as the perceptron is at telling iris species, but that is reasonably efficient at predicting whether somebody is going to live or die.
What's the error? I mean, is 46 significant?
To be honest, this was just a function I used in R. I don't know what it's outputting, and I don't know what the error is, actually. Does anybody know? Oh, good, we can all pretend we know. So it's essentially the standard deviation divided by n, and not n minus 1, obviously. So no, I don't know, I'm afraid. That's the number of iterations it had to go through in order to resolve that. So what I've done is try and show you how neural nets work, and I haven't made anything up. It is as simple as that. The complex bit is how you get it to run through the iterations to optimize those numbers without taking 4 million years.
So tell me, survival would be binary, 0 or 1. There's no in between. But actually, I think that this final neuron, you will have numbers that will not be just 0 and 1. So was it just if it's above 0.5, it turns it into 1, and if it's below it turns it into 0?
Yeah, absolutely. So this is going to output some number, And it's very, very unlikely to be exactly 0 or exactly 1. So you decide, okay, anything above 0.5 is survived and anything below is died. Now, of course, depending on what you're trying to do with a neural net, that could be rather bad. So you might decide anything above 0.9 is definitely this, anything below 0.1 is definitely this, and anything in the middle is not resolved. And if you're doing something like blood typing somebody before you stuff them full of blood, personally, I'd rather it didn't just go on 4.99 or 5.01. So how we use neural nets and how we apply them, there's a whole other lecture in that. But yes, you're absolutely right. This is outputting some value. Very often, actually, it'll be about 0.8, 0.9, or about 0.2 or 0.1. It often is quite a bimodal distribution, rather than just a normal. If it's a normal distribution, that would worry me. I'd expect it to be bimodal. Okay, so we have talked about how a perceptron works. This is just like a perceptron, except there are more neurons. And you'll notice that they're all interconnected. So this guy has a number coming in, but it has a weighted value going there, and a weighted value going there, and a weighted value going there. Every neuron here is connected to every neuron there. And that is the input layer there. That's the hidden layer. I could have 5, I could have 20 hidden layers in here. Can you see that the number of weights to be adjusted is going to be terrifying? And can you see that the number of iterations you would have to do is even more terrifying? I mean, I'm frightened just thinking about it. What the guys did with back propagation was work out an effective way of not having to go through this millions of times. And mathematically, it's a very, very clever piece of work. And that's why it took so long to get it working. This principle was known for a long time. Now, we come to the crunch. That is a neural net, and it functions moderately efficiently. What is it doing? Where are the rules? How is it deciding whether somebody is going to live or die? Now, you and I know that gender is very important. Imagine if we don't know. And somebody says, okay, why is it it says this person's likely to die. Why? I defy any of you to confidently point at it and say, well, I think you'll find it's because this is minus 5.99992 and not 6.02318. Because there's the model. That's it, that's the model. How is it deciding that? I don't know. And with this data, I use data we can understand on purpose. If I feed in data about fraud and not fraud in insurance, you'll get a load of numbers like this. You'll get input parameters like time of day and number of people involved. And there's the model. I'm not hiding anything. I don't know any more about it than that. And neither do you, neither do we. It's just a set of numbers. Now, it's interesting because you could train this, say, to spot fraud. You could develop an incredibly good model based on a massive amount of data. And you can simply save that model as those numbers. And the model here is the number of layers, the number of neurons in each one, all of those numbers, and that's the model. It's tiny. But that model is incredibly valuable. It's very saleable. But we don't know how it works. Unnerving, isn't it? And yet these things can be really, really efficient. Now, there are things you can do about this. I mean, for example, if I were to run this, so that's the model that I produced. Suppose I start afresh. Well, keep this model, but start again, generate the model again. But I leave out sex. I feed in 6 parameters, not 7. Given what you know, would you expect the neural net produced to be as good as this one or worse? It's going to be worse. And what does that tell us by inference?
That sex is an important variable.
Absolutely. It tells us that sex is an important variable. But it's only by inference. But we can do that. We can start playing around by inference. And if you leave out embarked, for example, it makes essentially no difference. So that tells you embarked is not particularly important. So there are ways we can do this, but this model is not understandable by human beings.
What percentage of the data did you use for this part of this?
Excuse me, can I ask you to use the microphone, please? Because then it's recorded and everyone can hear the question. Thank you.
What percentage of the data did you use to create this model here? Half, a quarter, or?
I use 70%.
Okay.
And then I use 70% to train it, and then I use 30% where I knew the answer and I fed it in, but I didn't tell the algorithm the answer.
Right.
I was sneaky. So then you can work out how efficient it is. And what I'm desperately keen for one of you to ask me is, why did you use 70%? But I'll leave that up to you. It's up to you. It's up to you. Can I assume somebody's going to ask it? Right. Well, I'll tell you, it's a very interesting thing. I think it's interesting. Everybody uses something like 70%, 75% for training and 20%, 25% for testing. Something like 70-30 is a really common split. And I run this master's course in Dundee on data science. And one of my students, a guy called Ian Brown, who is inherently a mathematician, was doing his project. And he said, right, I'm going to do a project on this. And he started. And Ian is absolutely meticulous. First thing he did is say, well, I'm going to need a training set and a test set. I need to split it on some ratio. He didn't just look at the books. He said, I'll go back to the original papers just to make sure I'm choosing 70-30 for a good reason. And he searched, and we can find no papers on this. All you find are people with books saying 70-30 is good. It says so in Donaldson's books. And Donaldson is saying, yeah, 70-30 looks about right to me. And it appeared that we could, now I'm not saying nobody's done it, but we could not find any original papers. So guess what Ian's project became? Much, much more interesting. What is a good split? And he did a very, very good project on this. So we do actually have good reason now to know about what split is about right. And it turns out that about 70-30 is right. But at least we know that. And that's why I wanted somebody to ask me, because I have good reason for doing it. Sorry, the question was, is this result published? And the answer is yes and no. Ian's master's thesis is a public document. We have not actually produced a paper, but it is published in the sense that it's a public document. If any of you want a copy of it, I'll happily, Ian said he's very happy for it to be distributed, which is true for most master's projects. So yeah, it's reasonably mathematical, but if you're a mathematician, that's fine. If anybody wants it, email me. If you can't find the email address of somebody with a beard called Mark Whitehorn who works at Dundee, really you don't deserve the paper. I mean, really, that's an investigation. I mean, I'll give you my email address, but you ought to be able to find it somewhere. So, where have we got to? I'm trying to convince you that that is all you get from neural net. Now, this is interesting because suppose we are, for example, let's choose a moderately neutral example, we're vetting people as to whether we should give them a loan or not. We train a neural net. It's very good at predicting whether people are going to pay the loan back. Somebody applies for a loan and we say, no, you can't have it. You can see where this is going, can't you? Because they say to you, why not? And you say, I don't know. The machine says no. And that's what it's coming down to.
Hi. Sorry, I was just curious. So in these cases, what would be the advantage of this over using like a regression technique?
Sorry?
What would be the advantage of using a neural network over a regression technique in these cases?
If you can do it with a regression technique, by all means do. Some things are, neural nets are good general purpose things. But I think if you can find a good other system that gives you a more understandable model, by all means do. Or use a neural net, but use several other systems that give a more understandable one so you get a clue, just as I've done here. So yeah, you know, I'm not advocating using neural nets for everything, but because they're so general purpose, I think they're going to be, and they will certainly do things that we can't do in other ways. That's certainly true. So, what rules is it applying? I don't know. I can begin to try and infer them, but that's not quite the same thing. So, welcome to the brave new world of the computer says no. Now, this starts at data mining, and it's going to cascade right the way up to machine learning, through machine learning, up into AI. And we can argue endlessly about what AI is, but let's, you know, it's going to end up there. And self-drive cars are going to run people over, and they're not going to be able to tell us why. I'm all in favor of self-drive cars, incidentally. I reckon they'll run over far fewer people than humans do. And just because a human can say, I ran over you because I didn't like you, and the machine can't tell you, I'd still like to have fewer people run over. So I'm not sort of saying this is apocalyptic and the world's going to end because we were using. I'm simply saying this is the state we're at the minute. And why did it take so long, in a word or actually two, back propagation? Big neural nets, and those are the only ones that can do really complicated things, just have trillions of combinations. And it's just mathematically very difficult to do. So, can we make neural nets even more complex? Oh yeah, you can make them as complex as you like. We just add more neurons and more layers. So there's my drawing of my nice simple neural net. Here is one that was used, and this is not one of mine, so I don't even know actually which way up it is, but let's not go there. It's a very interesting use of a neural net because, and I've just turned it on its side because you're going to see it working. You can do things with neural nets that you simply can't do with any other machine learning or data mining algorithm. Good example of that is you can take lots and lots of pictures of human beings and feed them through a neural net. And it will build up a set of weights which in some way encapsulate the essence of a human face. So this is no longer, are you going to get alone or not? This is, for human beings, a much more personal thing. That set of numbers that you saw, set of numbers up there, make it more complex. These are all layers, and these are all neurons, and every neuron here is connected to every one there. But it's still just a block of numbers. And train it with enough faces, and it gets to know what a human face looks like. And then you can feed it with numbers and get it to generate human faces that have never existed. And this is not taking a human face and tweaking the nose a little. This is generating whole new faces that do not exist in the real world. So, can we do that? Yeah, we can. I'm going to show you 6 faces. And what you have to do, one or more of them, is artificial. It is not a real person. I'm going to flick through them several times. And what you have to do is look for the ones that you think are not real people. 1 and 2, 3 and 4, 5 and 6. 5 and 6, 3 and 4, 1 and 2. Want to see them again? 3 and 4. Shifty looking guy there, don't you think? He's got glasses. That must be real, surely. It wouldn't generate glasses, would it? Okay. Who thinks number 1 is an artificial face? You are correct. Well done. How many people thought 2? You're correct as well. How many people thought 3? Well done. You know what's coming, don't you? All of these are artificial. These are not real people. I think this is quite incredible. You do get bizarre artifacts that come through instantly. There's oddity there. But what I find fascinating is this has not learned actually what a human face looks like. It's learned what a picture of a human face looks like. Because in that one, it's generated the background. And actually, it doesn't know what a human face looks like. It knows what a picture of a human face looks like, including the background. Isn't this spooky? I think this is spooky. So I was going to show you the URL first, but I think it rather gives it away. But you can visit that and see more examples of this. So what I want to do now, oh yeah.
Thanks. So this is a pretty simple question, but how do you know how many hidden layers you're going to need? Is that something you optimize for based on your model performance, or?
No, that is an absolute black art at the minute. So we don't know how to do that either. You can try it in various combinations, and people have, of course, tried to build artificial neural nets that predict how many layers you need for an artificial neural net. But that piece of code just suddenly disappeared. It just ate it, so I'm joking about that. It's a black art, and there is no way of predicting. You can have a good guess. You're not going to you're not going to build human faces from 2 layers of 4 neurons. But no, it's fascinating. I mean, one of the things I love about this is real science. This is the Wild West. You guys could make serious contributions to neural nets. People have brilliant ideas that nobody has thought of at this time. 20 years' time, it'll all be gone. All the good ideas will have been thought about. So I love this, and I think the URL's in the slides. But this is somebody who had the brilliant idea of using an artificial net to generate a face. That's not a real face. This is the neural net that was used to build it. And what they did was they started breaking the neural net. So that's the face as generated by that net. But that net is a set of incredibly, well, I was going to say carefully chosen numbers, but chosen by a neural net's piece of software, not by a human. But the balance of the numbers is crucial. And what they've done is they've started knocking out numbers and replacing them with random numbers again. And this is illustrating the point that the whole face is somehow in that block of numbers. Because if you knock out a number, the nose doesn't suddenly disappear. It's not that. It's not just each number, it's that number in concert with the other numbers somehow. So what I'm going to do is run this, and you'll see some of these turning red as they're knocked out, and you'll see the effect it has on the face. If you have a nervous disposition, don't watch this. So you can see some of these are being taken out, and you can see the effect it's having.
It's almost like genetic engineering.
I mean, it's almost like the skull is emerging, isn't it? It can't be. It doesn't know about the skull. And there's quite a good poem goes along with that on that page. But I think it's a really good illustration of the fact that these neural nets are weird. The numbers somehow in concert are encoding information. It's not just one number. So there are lots of new and exciting technologies coming in. Things called autoencoders and generative adversarial networks. And I mention these just in case you guys are interested in reading about other stuff. That's more or less an hour. I've got a bit more stuff on these things called autoencoders. Will you feel A, cheated if I don't talk about them, or B, annoyed because I run over time? No, one of my obsessions is you do not run over on talks. I hate people who do it. Because if you're talking after them, you see your slot eroding as they go on and on and on. But we can, if you like, I can do a bit more on autoencoders, because they are fascinating. So why are we talking about these things? Yeah. Oh, something else. If you're interested in trying to work in the work that's being done to try and work out how neural nets are working, look up this thing, local interpretable model agnostic explanations, thing called LIME, and that's quite an interesting attempt to understand neural nets, understand why the numbers are as they are. Self-drive cars, summary. I've really talked about all of this. So I'll talk a bit about autoencoders, and this work is not my work. This is the work of Kate Kilgour, who's one of my PhD students. And so I have shamelessly stolen her slides, except I'm telling you I've stolen them, so I haven't stolen them. And Kate is working on this. So autoencoders are kind of based on the idea that you can build a neural net. And I don't want to go into too much detail here, but you can build a neural net which compresses down to a very small number of neurons in the middle and expands outwards. So you might take some input numbers, and then you try and reproduce those numbers. Now this, on the face of it, is stupid, because we know what the numbers are. Why are we trying to reproduce them? We can just get the table. But bear with me on this. That means that you can take something like a photograph. A photograph is just a load of pixels. You can stuff those pixels into an input layer. You need quite a big input layer, but you can do it. You stuff them in, you reduce it down to a small number of neurons, and you see how good a picture you can get back out at the other side. Again, this may seem a little pointless, but this is what academic research does. So you encode the values that you get, not the weights now, but the values in those nodes, in that reduced layer, are an encoding of that original picture. And basically, the neural net reduces down like that, and then it goes up. And typically, the weights are symmetrical on both sides. It's a reduction to an encoded value, and then taking that encoded value and building it back up to the total number of pixels. So can we do this? Yes, we can. And this means that we can encode information. And we talk about that as the encoder and that's the decoder. But bear in mind, they're typically symmetrical. One is the mirror of the other. Well, okay. Kate was playing around with this. And there's a set of fashion images which are available. And these are the original input images. She fed that into a neural net which compresses down to a hidden layer of only 2 nodes, and then expands back out. And you can see that there's quite a lot of information being lost here. The idea of this exercise was not to encode as accurately as possible, but to reduce the number in that middle layer down to just 2 values. And she successfully did that. But what she then realized was that if you have just 2 values in there, you have just 2 nodes, you can actually plot that on an XY graph. Because it's just 2 values, you can treat one as the X and one as the Y. And that means that what's happening is you can look at each image and you can see up there is the input image, and they're not particularly good quality input images. Down there is the output. But then you can start playing around with this, because you can say, well, if you feed that in, you get that X coordinate and that Y coordinate. And when you pull that out, you get that. And that meant she could explore that 2-dimensional map. You could feed in every possible combination of those simply into the decoder and see what you got out. Because clearly, if you take that shoe, you feed that in, you get values up here. The value you get out from that combination is that. But you can ask the question, what image would I get from there? And what image would I get from there? So you can map that 2-dimensional space and say, what images does it have in it? Now, just to be clear about this, the only reason those 2 numbers decode to that those two numbers decode to that, is because they were trained with those images. I'm not saying that that image is inherent in those two numbers. It's only inherent in those two numbers because the system was trained. But what you can do is say, well, let's just put a grid across that and see what shapes we get. And you can see shoes morphing into trousers, and I bet you've never seen that before. You probably never want to see it again. But you have this compression right down to just two numbers. And those two numbers are encoding this information in some way. And what you could also do was map, these are where the real image is. There are 10,000 images. Those numbers only go in there. There is no image there that encodes for those numbers. But there's nothing to stop us exploring that space, which didn't even exist in the original input data. So, Almost Unreal? Anybody know the Roxette song, Almost Unreal? You're all too young. Yeah. Anyway. Let's think about this. This is fascinating. But if you take, for example, a load of data, suppose the government says to you, you can't use real customer data. Okay, fair enough. Suppose we take a load of customer data and we train an autoencoder. And it takes all those customers, squeezes them down to 2 dimensions, could be 4, but it doesn't have to be 2. 2 visualizes very nicely, of course, and then expand it out. Once you've trained that model has the essence of customer somehow in it. And if you take that 2-dimensional space and plug in numbers that are not your customers, they're not real people. In fact, you studiously avoid any actual numbers that were encoded by customers, and you feed in numbers close to, but not those. They will expand out to give you a set of customers who've never existed, and yet have exactly the same behavior as your customers. Are you stealing their data? Discuss. What distresses me about this is we have governments, we have people who are supposedly managing this. I would not like to explain that to an MP. I'm not running down yes, I am actually. You guys are interested in data. You have a huge background in data. I hope you can understand this. Explaining that kind of conundrum to people and expecting legislation to be brought out before that happens, forget it. But I think there is a whole interesting area here about generating data. And autoencoders are a fascinating way of doing that. And this is reasonably leading edge. You know, and I don't know of anybody, for example, generating customers. That was my idea. I don't know of anybody doing it. But you can think of all sorts of stuff other than customer data. So these things are going to change our lives in all sorts of ways. And I really, really would recommend, if you're interested in these things, read about them. And these things called GANs are fascinating. That's an idea that a drunken PhD student had at the pub, went back to the lab and said, I'm sure this will never work, was there till 4 in the morning, and it did work. And it's a whole new area of neural nets. So that's about it. Thank you very much for listening.